Hi everybody, Newland here. Let's talk about RC circuits and how we are supposed to describe the charge as a function of time, the current as a function of time, and the voltage as a function of time. I have a diagram here with a switch, and imagine a scenario where we close the switch between the top branch and A, as opposed to closing the switch between this branch and B. So imagine this scenario here. The voltage that we have here, the EMF, is going to drive charge onto the capacitor. And if this guy is closed like that, then you can imagine electrons building up on this plate. So this would be the negative plate, and this would be the positive plate. You can also imagine positive charge flowing this direction in the conventional current sense. So you can think of the clockwise flow of current so that this plate becomes positive. In this scenario, there's a resistor, and the two work together in a way that is not as obvious as when you do like a Kirchhoff loop or a junction rule or even capacitors themselves with batteries. When you combine the two together, it becomes more complicated. So let's do a loop. So imagine we start here and we work our way around that way. So I'll remind you when you do a Kirchhoff loop problem, if you end up trying to determine the current in a particular circuit and it becomes negative, then you made the wrong decision. But that shouldn't be a problem here based on the way we've set this thing up. And Kirchhoff loop says the sum of all the voltages in that loop will be zero. So starting here, we have a positive potential difference. So we went from negative to a positive, so plus E. The capacitor will end up with this being the positive side and this being the negative side. So once this thing does reach its full charge, meaning that this thing will reach the potential of our battery, then it's going to actually act against this loop. So we describe that actually by saying Q over C, where Q over C is voltage at some time t. That's, by the way, why I used a lowercase q here. So the EMF is going to be assumed to be a constant, so it's driven by something like an Arduino board or a battery at a certain voltage. The charge is going to build from 0 up to a maximum charge, and the capacitance is a constant based on the geometry of the particular kind of capacitor you're using. So that's the battery, that's the capacitor, and then there's going to be a potential drop of I times R as current goes across the resistor. So we've got here normal algebraic Kirchhoff loop sort of scenario, but at the moment when we close the switch before any charge is actually built up, this expression is actually 0, so you end up with EMF over the resistance. That's the initial current, I sub 0. And that particular value is going to be the highest the current's going to be able to go in this circuit, and that only will happen as soon as you turn it on. As soon as any amount of charge at all starts to build up on the capacitor, the current will be less than I sub 0. So this is also the, or I naught, it's also the maximum current we're going to have. It's also kind of useful if we write down what the maximum charge is going to be. And that's going to be C times E. So the maximum charge this thing is capable of holding, based on the way we've designed the circuit, is the capacitance times the EMF. So we're going to call that Q max. And these are some of the components we're going to end up using here. So we can take this expression up here, E0 equals E minus Q over C minus I times R. Notice we use lowercase I here because it's also less than, so lowercase q is less than q max, and lowercase I is less than I sub 0. And they're both going to be functions of in with respect to time. And we can actually take the I and turn that into a function of relating charge and time directly as well. Let's do that actually. Let's move the IR to the left-hand side. So that equals E minus Q at some time t over C. And we make a couple of notes here. our ultimate goal is to get charge on one side, on the left-hand side of our expression, and time on the right-hand side. And we haven't gotten very far into this process, but I want to make sure to note that that's our ultimate goal. It's important to know that the infinitesimal change in charge as a function of time is the infinitesimal current. So dq dt is I. So I can rewrite this thing as dq dt times r equals e minus q over c. So far, so good. We can also take this expression and simplify it a little bit, which is really a matter of practice, knowing when to do this. And right now, what we've got in the way this thing is set up, we've got an r right there, and well, let's divide both sides by r. So, in fact, we could say that dq dt, which is nothing more than current, is going to be e over r minus q over rc. And I would also, since we're making a list of things that are commonly mentioned here, we often call r times c the time constant tau. So we could replace this with a tau right here. But let's not do that yet. So looking at this expression, e over r minus q over r times c, if we multiply this expression, e over r, by c over c, it makes it actually a really useful expression that'll help us do separation of variables with this differential equation. So c times e, notice this is just q max right here, by the way, over r times c minus q over r times c. So now we have a common denominator. And that allows us to rewrite this expression as dq dt equals ce minus q over rc. And before we do anything else, if we multiply this expression by -1, the ce minus q, then if you're kind of looking ahead and you're thinking about this in a calculus sense, we've got a dq over here, and we're going to have an expression on the top that has a q in it. But if you've done derivations like this before, it usually becomes helpful to not have the negative sign in front of the q if you've got a dq. So when we go to do our integral, ultimately that's actually going to make it a little bit harder to do. So let's actually say -1 over rc, and then we're going to actually make this q minus ce. So that we've factored out the -1 to change this expression to q minus ce. So we flip this guy over there, and we're leaving the -1 there. Well, it actually is in a kind of handy form right now. We can divide both sides by this expression. So we'll have 1 over q minus ce times dq dt equals -1 over rc. And if you've done separation of variables before with this kind of expression, you know that what we're supposed to do is integrate both sides with respect to time. In fact, I'm making a mess of that. Let's clean that up slightly. So dt equals dt. And when you integrate this dt over dt, these two infinitesimal changes in time, essentially they go away. And so now I'm left with, and we're in sort of an ambiguous state right here. We want this to go from 0 to time t, but this expression, if we rewrite it as the integral from 0 to some charge q less than q max, and then we've got dq over q minus ce, and then we can leave the right-hand side as it was before. That's the integral from 0 to some time t, and again, that's less than the amount of time it takes to reach the maximum charge. And we've got -1 over rc dt. And it probably would help to take this right-hand side, move the -1 over rc out, and now we've got integral from 0 to t dt. My t is really sad. That's okay. And the expression on the right-hand side is then 0 to the integral from 0 to t, the integral of dt from 0 to t, excuse me, is just t. So the right-hand side becomes t over rc. And the left-hand side, which I'll rewrite here for convenience, 0 to some charge q less than the max, dq over q minus, that's a minus sign, minus c times e. By the way, this is just the maximum charge. Remind you of that. This looks almost like a natural log sort of integral, but we don't want to mess it up. So we've got dq over q minus ce. You can write that as the natural log of q minus ce, and the limits are going to be from charge 0 to some charge q. And typically you would need absolute value bars here, but our physical scenario is such that this expression can't be negative. That's the way this is going to end up working isn't going to be possible. So I'm also just kind of lazy, which is also a fair way to say it, if I'm honest. And I got negative t over rc, and I'm not always honest. So if we use our limit notation here, we can say natural log of q minus ce minus natural log of 0 minus ce equals negative t over rc. And this expression here, natural log of 0 minus ce, this is natural log of negative ce. So, and when you're subtracting two quantities, you can, this quantity divided by that quantity, if you're subtracting two natural logs, it's simply the natural log of the ratio of the quantities. Meaning I can rewrite that as natural log of q minus ce all over negative ce. So when you subtract two natural logs, you can divide the two ratios, but this guy's simply 0, so that's negative ce. And we're going to drag along our time over rc for the ride, because it's enjoying itself. So this expression here needs to be simplified. In fact, what we're trying to do is get a function of q with respect to time. And by doing that, we can then get to voltage, and by doing that, we can then get to current. All right, so we need to exponentiate both sides. So e to the for both of these. And e to the natural log of stuff is just stuff. So q minus ce over negative ce equals, and now we've got an e to the negative t over rc. And this expression, when t is 0, when I plug in 0 right there, that would be the equivalent of e to the negative 0, or 1 over e to the 0, but that's just 1. And as time goes really, really large, as time goes to infinity, this expression then becomes 0. And remembering that when you're doing one of these derivations generally makes it easier to follow through as you're doing sanity checks and whatnot, making sure that at the limits at time 0 and time t that it does what you want. So I'm going to multiply both sides by negative ce to simplify this. We're trying to solve for q after all. We're nearly done. Aren't you excited? Okay, so I can add ce to both sides. So q now equals ce minus ce times e to the negative t over rc. I'll remind you that c times e is just q max. You guys getting tired of hearing that yet? So q now is c times e, and I can factor that out. 1 minus e to the negative t over rc. And we can replace a couple of these expressions. So q max is c times e, and tau is r times c, and this is called the time constant. And if we do that, then we get an answer where q is a function of time is q max times 1 minus e to the negative tau, whoa, my t got upset there, e to the negative t over tau. And like I said before, when t is equal to 0, we actually have no charge at all on the capacitor. And when t gets really, really, really large, this expression becomes 0, and we're left with q max. So that is one of our goals. So we've actually got here one of our expressions. Q is a function of time in terms of some universal constants. It's also worth talking about what happens when t actually reaches tau, so that the exponent t over tau, which would be tau over tau, which would be e to the negative 1, which is 1 over e, that value, we talk about that a lot when we're using RC circuits. I added an extra highlight there. Not that it wasn't pretty, but that's what I meant. Okay, So remembering that Q equals C times V, which means that Q over C is V, remembering that, we can actually take our yellow expression, which is, it's actually quite lovely. We can divide the entire thing by C, or both sides by C. So Q over C equals Q max over C, and we still have the 1 minus e to the negative T over tau. So that's not going anywhere. The left-hand side over here is now the voltage as a function of time. And the right-hand side, which is Q max over C, that's just our EMF. 1 minus e to the negative T over tau. It's supposed to be a tau. It's an ugly tau. Not to hurt its feelings, but I could do better. There. So what this means is the potential difference, or I guess the voltage on the capacitor would be a better way to say it. The way this works, when t is equal to 0, there's no voltage. There's no charge, so no potential difference. And eventually, as t gets really, really large, we end up with a charge of E. And if we go back and look at our circuit, here's the interesting thing about having a capacitor in a circuit like this. At the time when we've reached the maximum charge, once the charge on this guy goes to Q max, that means the potential difference is E. And if we have E right here, and essentially it would have to be negative E based on the way we drew our loop like that, well, we have no potential difference across the circuit as a whole. So current's going to stop. So we should actually be able to show that current will eventually go to 0 and start out at I sub 0. I'll remind you that we started at I sub 0. It should actually go to 0 when we're done. So if we come all the way down here, and you probably saw that I is dq dt. So if we go back to our expression for charge, which is what we had a minute ago, that was Q max times 1 minus e to the negative t over tau. Wow, that tau looks like a drunk person did it. Terrifying. That's better. All right, so we can actually take the derivative of this guy. So dq dt, which is literally the current, is derivative with respect to time of Q max times, I'm going to switch to square brackets here, e to the negative t over tau. And the Q max, notice that we're going to have to differentiate this expression with the square brackets. But this guy's a constant, so it ends up out in front. So I equals Q max times the derivative with respect to time. Go back to parentheses now. 1 minus e to the negative t over tau. We're differentiating with respect to time. Well, 1's a constant, so the derivative of that with respect to time is 0. So what we really need to do is take the derivative of this expression here. So we know that that's 0. So we can simplify this a little by saying I equals negative Q max. We can actually take that negative sign right there and move it out in the front, times derivative with respect to time of e to the negative, oops, my line went wonky on me. So that's supposed to be e to the negative t over tau. And you need to take the derivative of the exponent before taking derivative of the function. But the derivative of the exponent is negative 1 over tau. It's actually negative 1 over tau dt over dt. So you end up with negative 1 over tau. So the derivative of the exponent is negative 1 over tau. So I equals negative Q max, that hasn't gone anywhere, times negative 1 over tau. Remember, this is R times C. It's called our time constant. It also doesn't like for me to draw it. It's clearly not my fault. It has a mind of its own. And the derivative of the function, derivative of e to the x is e to the x. So derivative of e to the negative t over tau doesn't really go anywhere. So we could simplify this slightly. I equals, now the two negative signs cancel each other out. So now I've got Q max over R times C And there's a reason why I broke up tau back into R times C times e to the negative t over tau. So I'm going to leave that tau there, but I broke up the other one. And I want you to notice that we've got Q over C again, so that's E over R. So I, as a function of time, is now, we've got E over R. Q max over C is E over R, times e to the negative t over tau. And I also will remind you that E over R, when the switch was first thrown and there's no charge at all, that's I sub 0. So I as a function of time is the initial current, or I naught, I guess, times e to the negative t over tau. And we have here an expression for current as a function of time. And if we look at this, where t is equal to 0, we'll see that we get, when you plug in 0 for t, that's e to the negative 0, so that's 1. So initially we have nothing but I sub 0. And when t goes to infinity, as t gets larger and larger, this expression goes to 0, and we have no charge at all, no current at all in the circuit. We forgot, by the way, to highlight this expression, and I like highlighting. So we actually found 3 different expressions here using the separation of variables and differential equation stuff. We found charge as a function of time in the capacitor, voltage as a function of time in the capacitor, and the current as a function of time for the capacitor. And both current and voltage are something that are fairly straightforward to measure in a circuit when you build it yourself, especially if you have a microcontroller like an Arduino, whereas charge may be harder to actually find in most scenarios. All right, there you go.